You clicked because you know the power problem is real, and you are right to be concerned. The bottleneck is not in the algorithms, but in the silicon that tries to run them. Current hardware wastes energy moving data far more than it spends computing it, a flaw that makes untethered mobile robotics impossible today. By the end of this explanation, you will understand why analog memory computing is the only architecture capable of solving this fundamental constraint. Consider the physical reality of a mobile robot trying to process sensor data in real time. In a conventional digital system, the processor and memory are separate. Data must travel back and forth across a bus every single time a calculation is needed. This movement consumes the vast majority of the system's energy. Research indicates that conventional systems waste 10 to 100 times more energy moving data than they do performing the actual computation. For a desktop server, you can solve this with massive cooling and a constant power cord. For a drone or a mobile robot operating in the field, that approach is physically impossible. The battery drains instantly, and the heat generated would cook the electronics before the mission is complete. This is where the industry is hitting a hard wall. We have software that is incredibly smart, but the hardware cannot execute it without tethered power or massive cooling systems. The von Neumann bottleneck, the separation of storage and processing, is a physical limit that current silicon architecture cannot overcome for edge devices. We need a system that does not move data but computes where the data lives. This is the promise of analog in-memory computing. The core concept here is a shift from compute, then store to compute, while storing. In a standard digital memory array, bits are static. You read a value, move it to the processor, calculate, and write it back. In an analog in-memory computing architecture, the memory cells themselves perform the math. When you apply voltage patterns to a memory array, the physical properties of the materials allow the array to calculate directly. This enables massive parallelism. Instead of processing one number at a time, the entire array processes thousands of operations simultaneously in a single clock cycle. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. TetraMem has introduced a specific approach to this problem using a capacitor gain cell architecture. This design enables dynamic associative processing with frequent memory updates. Most analog memory technologies, like ReRAM or FFET, struggle with endurance and write speed. They cannot handle the rapid changing data from sensors without wearing out quickly. TetraMem's architecture solves this endurance bottleneck, allowing the memory to handle real-time sensor streams without requiring a tethered power source. This is critical because mobile robotics relies on dynamic data, not static datasets. The implications for energy efficiency are staggering. Benchmarks indicate that for specific convolutional layers, large-scale analog macros can significantly outperform digital counterparts in energy efficiency. The reduction in computational costs can reach orders of magnitude. If we can reduce the power envelope to sub-watt levels, we unlock the possibility of long-duration autonomous operation. A robot could theoretically run for days on a single charge, processing complex visual data without overheating. This is not just a speed hack. It is the only architectural path to true edge AI that operates independently of the grid. However, there is a critical trade-off that engineers must confront. Analog circuits suffer from inherent noise and device variation. In a digital system, a bit is either a 1 or a 0. In an analog system, the signal is continuous and susceptible to interference. This noise can compromise accuracy compared to the perfect precision of digital systems. If you are running a financial calculation, this might be a deal breaker. But for robotics and computer vision, the requirements are different. This leads to a profound shift in how we design these systems. We must now design for hardware non-idealities as part of the algorithm rather than treating them as errors to be corrected. This is a paradigm shift that changes the software-hardware co-design requirements for robust edge AI systems. Instead of fighting the physical quirks of the material, new techniques like differentiable spike-time discretization are beginning to harness these physical quirks. The noise is no longer a bug. It becomes a feature that the system can learn to utilize. It is also important to recognize that this technology is not a universal silver bullet. Research suggests that while analog in-memory computing excels in spatially unrolled workloads, digital in-memory computing remains superior for depth-wise layers with limited unrolling opportunities. The viability for mobile robotics depends entirely on the specific workload characteristics. You cannot simply swap a digital chip for an analog one and expect it to work everywhere. The current adoption is limited by the need for sophisticated peripheral circuitry to manage these non-idealities. Engineers must build robust analog-to-digital interfaces that can translate the noisy analog world into clean digital decisions. The market response reflects the urgency of this problem. Projections indicate the market for this technology will grow from $51.9 billion to over $1 trillion by the year 2032. This growth is driven by the desperate need to solve the power density crisis that makes current silicon-based AI infeasible for battery-constrained mobile robotics. We are moving toward a future where the hardware itself is intelligent, not just the software running on top of it. The engineering challenge now is to master the interface between the physical world and the digital logic. We must build systems that can tolerate the imperfections of analog physics while delivering the reliability required for autonomous operation. This requires a new mindset where the hardware and software are co-designed from the ground up. The goal is to create machines that can think and act in the real world without being tethered to a power outlet or a cooling tower. The path forward is clear. We must embrace the physical realities of analog computing. We must stop trying to force digital precision onto analog materials and instead learn to work with the physics of the materials themselves. This is the only way to achieve the sub-watt power envelopes required for the next generation of autonomous systems. The technology is emerging, the benchmarks are promising, and the need is urgent. The future of mobile robotics depends on this architectural pivot. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.